In this class, we are going to be studying equilibrium for the next 3 chapters. Chapter 13 lies the foundational groundwork so that we can understand some of the advanced equilibrium topics in later chapters. Whenever you do a chemical reaction, there are 2 important questions to consider. How fast does the reaction proceed, and how far does the reaction go? The first question of how fast is a question of kinetics. We tried to answer this in the previous chapter. By writing rate law equations and studying the integrated rate laws, we were able to see how reactions proceed as their concentration changes. In this chapter, we're going to learn how far a reaction goes, which is a question of position of a reaction and a question of equilibrium. A reaction could lie far to the left, we would say, meaning it's a reactant-favored equilibrium and it doesn't form very many products. Or a reaction could lie far to the right. In this case, it would be a product-favored equilibrium, and it would form a lot of products and there wouldn't be very many reactants left. Or it could kind of lie in the middle. In that case, you could have a reaction that has about an equal amount of reactants and products. Equilibrium will answer how we can predict the position or how far a reaction will go. Throughout the course previously, we've seen a few different types of equilibrium so far. Phase equilibrium, where you are in between 2 phases, fusion and freezing, vaporization and condensation. Those are examples of dynamic equilibria. For example, if we have a bottle and we close a cap on it, eventually evaporation rate and condensation rate will become equal within that closed container. This is an example of a dynamic equilibrium, where particles in the liquid state are still evaporating, and particles that are in the gaseous state are still condensing, but it's doing so at the same rate, so it appears that there's no change overall. Another type of equilibrium we've briefly discussed is solubility equilibria. If we have a saturated solution, that means that the rate of crystallization is equal to the rate of the dissolving reaction. In this chapter, our main focus is going to be on chemical equilibrium. A chemical reaction has reached equilibrium when the concentrations of the reactants and the products remain constant over time. Or in other words, the rate of the forward reaction will equal the rate of the reverse reaction. So imagine that we have a reaction, A going to products, B. The rate of the forward reaction of A turning into B is going to slowly start decreasing as A goes away. And the rate of the reverse reaction of B going back to A is going to start increasing as soon as B is formed. Eventually, the 2 rates of those reactions will become equal. Once they're at that equal state, then the reaction has reached equilibrium. We can also think about what it would be like for the reactants and products going away and forming with time. The reactants are slowly being used up as A is going away and B is formed. And B is slowly being formed as A goes away. So the amount of A goes down while the amount of B goes up in this case. Once they reach that steady state where there's no change in the amounts of A or B, everything to the right-hand side of our dashed line represents the chemical reaction being in equilibrium. Chemical equilibrium is said to be a dynamic rather than a static process. Dynamic means that reactants are still reacting and becoming products. Products are still reacting and going backwards and becoming reactants. It's just that there's no change in the amounts of them since the rate that it's happening is equal. Double arrows are used to indicate a reaction that is reversible. So we use double arrows to represent reactions that are in equilibrium. Previously, we would have seen this for weak electrolyte solutions. We would have used double arrows to indicate the dissociation or ionization of a weak acid or a weak base. Some examples are an acetic acid solution, which is a weak acid, or an ammonia solution, which represents a weak base. So let's recap. How would we write the ionization of the weak acid, acetic acid, in water? So we would write first our formula for acetic acid, HC2H3O2. And how will that acid ionize if we put it in water? It's a weak acid, so it's only going to partially ionize, and that means we would use double arrows to represent the equilibrium that would be set up from that partial ionization. The proton out in front of the acid is the proton that will be donated and picked up by the base. In this case, the base would be water. We would form the hydronium ion, H3O+, when water picks up that proton from the acid. And we would form acetate anion, which is left over when acetic acid loses its proton. So at equilibrium, if we have a flask of acetic acid and water, we don't just have hydronium ion and acetate anion present. Instead, we have some combination of molecular acetic acid, water molecules, and the products that we were forming. Most of this acetic acid does not ionize, so most of it will be present as its molecular form. Only a small amount of it will be ionized into the hydronium ion and acetate anion, so we say partial ionization. Compared to strong acids, which fully ionize 100%. Hence, for a weak acid, this is why we would use equilibrium arrows to represent that. The same idea can be used if we write the ionization for a weak base. Weak bases only partially ionize. Ammonia, or NH3, is a weak base, and if we put it in some water, there will be a small extent of ionization. The ammonia will actually pick up a proton from the water, and it'll form the ammonium ion. This is because the water is acting as an acid in this case, and the ammonia is acting as a base. The base will abstract a proton from the acid. And when water loses a proton, it's left with the hydroxide anion, so it has a negative charge. This is also a process where we have partial ionization. And so in the flask, what's present at equilibrium is mostly molecular NH3 and mostly water, which is also a molecule. And there's a little bit of the ammonium ion and a little bit of the hydroxide ion. Whereas normally we expect the reactants to react fully and form products, that's not what's really happening with all reactions. And so those double equilibrium arrows are expressing that we have reactants and products present at equilibrium. For any reaction that's in equilibrium, we can write something known as the equilibrium expression or the equilibrium equation. Those two terms really mean the same thing. If we imagine we have a reaction, A plus B forming C plus D, where the little letters out front represent the coefficients of the balanced equation, the equilibrium constant, K sub C, is defined as the ratio of the product concentration over the reactant concentration. When we actually plug in our products and our reactants into our expression for K sub C, we have to raise them to the coefficients from the balanced equation as exponents. So in our numerator, we're going to have the concentration of product D, and that will be raised to lowercase d, which is the coefficient for that, times the concentration for product C, and that'll be raised to the exponent of the coefficient lowercase c. So that represents our products over our reactants. We have reactants A, so concentration of A raised to the coefficient lowercase a, times the concentration of reactant B, and B will be raised to its coefficient lowercase b. Recall that the brackets mean concentration in molarity. So those are in units of moles per liter. And our lowercase c on our equilibrium constant, K sub C, also means concentration. The equilibrium constant is written without units, and it is temperature dependent. So in a lot of the problems, they will specify a temperature, but you don't actually have to use it. Just understand that the equilibrium constant will change as the temperature of a reaction changes. The right-hand side of our equilibrium expression has a name. So this fraction right here is often referred to as the mass action expression. Whereas the whole thing together, when we write K sub C is equal to the mass action expression, is referred to as the equilibrium expression or equilibrium equation. If we were to take our chemical reaction from the last slide and flip it around, so now that our products are written as reactants and our reactants are written as the products, we could write the equilibrium expression for this reaction as well, the reverse direction. In this case, we would call it K sub C prime. Prime means that the reaction has been flipped around. We still take the ratio of the product concentration raised to the coefficients from the balanced equation over the reactant concentration, but now our A and B are in the numerator and our C and D are in the denominator. So that's one way that we could calculate K sub C prime. Or to get K sub C prime, we could simply take 1 over K sub C, since it's going to be the inverse of our original reaction. Because of this, whenever we are writing an equilibrium expression or equation, we have to have a balanced equation that relates to that, so we know specifically what equation we're talking about. Write the equilibrium expression for each of the following reactions. In the first one, we have nitrogen plus 3 moles of hydrogen forming 2 moles of ammonia. So we're going to say K sub C is equal to the concentration of our products, which is just the ammonia, NH3, and we want to raise it to the balanced equation coefficient, so the ammonia will be squared, and that'll be over our reactants. So one of our reactants is N2, and that would just be to the first power because there's a 1 out in front of the nitrogen. You don't have to write that though, times the concentration of the hydrogen, and the hydrogen we would want to cube because in the balanced equation there's a 3 out in front of it. So this would be our equilibrium expression or equilibrium equation for our first reaction. And now notice in the second reaction, it's flipped around. So this would represent that reaction's K sub C prime. And we could say on the top, the products are nitrogen to the first power times hydrogen, and that would be to the third power, over our only reactant, which is the ammonia, NH3, and that would be squared. So still using those coefficients from the balanced equation. But you can see here that it's just the inverse of the original K sub C. So really K sub C prime is equal to 1 over K sub C, the original equilibrium expression. If we actually know equilibrium concentrations for our reactants and products, we can substitute them into the equilibrium expression. So in this case, we want to calculate the equilibrium constant, K sub C, if we know that the equilibrium concentrations of nitrogen is 0.03 molar, hydrogen is 0.027 molar, and ammonia is 0.016 molar. So what's important is that these are equilibrium concentrations, and not just any random concentrations. You can only substitute equilibrium concentrations into the equilibrium expression to calculate the equilibrium constant. So on the left-hand side, we have our nitrogen plus hydrogen forming ammonia, and this is the equilibrium expression that we wrote previously. So we're going to take our equilibrium concentrations and plug them in. K sub C will be equal to the concentration of ammonia, which is 0.016 molar, squared over the concentration of nitrogen, which is 0.03 molar, times the concentration of hydrogen, 0.027 molar, and hydrogen is cubed. So we can solve for K sub C by figuring out everything on the right-hand side of our expression. And K sub C comes out to 434 for that first reaction. And it's recorded without any units at all. We could also do the same thing for our other reaction. K sub C was equal to the nitrogen concentration, which is 0.03 molar, times the hydrogen concentration, 0.027 molar, and that had to be cubed, over the ammonia concentration, which is 0.016 molar, and the ammonia was squared. This would represent K sub C prime because it is actually the inverse of our first reaction. So when we calculate this, we end up getting 2.31 times 10 to the negative third. The other way to calculate K sub C prime then would have been to take our original value and take the inverse of it. So 1 over k sub c. If we do 1 over 434 that we got in the first part, that gives us the exact same value, 2.31 times 10 to the negative third. So there's two ways to go about that. There is another equilibrium constant that is sometimes used for reactions that contain gases. The equilibrium constant K sub C that we were previously using, the lowercase c meant concentration. So we used molarities to calculate K sub C. When we're calculating K sub P, the P means pressure. Therefore, we're going to be using gases and their units will be atmospheres. Imagine we have a reaction of gas A going to gas B, and it reacts with the coefficients lowercase a and lowercase b. We can write the equilibrium expression K sub P will be equal to the ratio of the products over the reactants. And we'll still have to look at the coefficients for our balanced equation. But in this case, we're going to say that the partial pressure of gas B raised to the superscript lowercase b from the balanced equation over the partial pressure of gas A raised to lowercase a, which is our coefficient from our balanced equation. When we plug in atmospheres into this equilibrium expression for our partial pressures of our gases, we end up getting K sub P as our equilibrium constant. It's still written without units, just like K sub C was, but K sub P and K sub C are not equal to one another. There is a link between K sub C and K sub P, and we can derive that link to come up with an equation that allows us to solve for one or the other. We previously learned the ideal gas law, PV equals nRT. And the ideal gas law actually tells us that the pressure is directly proportional to concentration and molarity. So imagine that first we take our volume term and we divide both sides of the equation by that. And we're still going to look at this imaginary reaction of A going to B, and both of them are gases. So we could write the ideal gas law for A and talk about the partial pressure of A, and we could do the same thing for component B and talk about the partial pressure of B. So the partial pressure of A is equal to the moles of A divided by the volume times R and T. The same thing with the partial pressure of B. That'll be equal to the moles of B divided by the volume times R and T. This term right here, moles of A over volume, is just equal to the molarity of A. So we can rewrite that as concentration of A using our familiar term of brackets around it. The same thing with N sub B over V. That's moles per volume in liters. So that's also going to represent the molarity of B. So we can rewrite that as the brackets surrounding B to represent molarity. Now we have the partial pressure of A as the molarity of A times R times T, and the partial pressure of B as the molarity of B times R times T. Our reaction is going to be in the same flask, so it will be at the same temperature. And R is a constant, so that will be the same as well. That's the gas constant. In this case now, we can rearrange our equation by substituting them in to what we know the equilibrium constant K sub P is. We would write the partial pressure of B raised to the B power, that's the coefficient, over the partial pressure of A raised to the A power, which is our coefficient from our balanced equation. So the lowercase a and b represent those coefficients. So now we know what partial pressure of B is. We derived that. We're going to substitute that in. Same thing with partial pressure of A. We derived that, so we could substitute that in. Still raising them to the exponents, lowercase b and lowercase a. Pulling out then that R and T term, because those are constants, they're the same for the reaction. That leaves us with B over A, each raised to the little b and the little a, times R times T raised to B over A. And when you have exponents that are raised to one another and they're divided, you can end up subtracting them. That's a rule of exponents. So this derives essentially a link between K sub P and K sub C because this term right here is equal to K sub C. That's just our molar concentrations. And then they're factored by one another to this RT term raised to the B minus A. Well, B minus A is often abbreviated as something called delta NG, where delta NG equals the change in the number of moles of gas. So we want to look at the number of moles of gas on the product side and the number of moles of gas on the reactant side. Gases are really the only thing that contribute to the pressure substantially. So K and C and K sub P are going to be different for one another in reactions that involve gases or change in the moles of gas. Delta NG can be calculated by taking moles of gas on the product side, which we can refer to as some final state, minus moles of gas on the reactant side. So there will just be some number that we plug in for delta NG when we take the difference in those number of moles of gas. For the reaction, water plus methane forming carbon monoxide plus 3 moles of hydrogen, if K sub C is equal to 3.8 times 10 to the minus third at 1000 Kelvin, what is K sub P at the same temperature? So we're going to use that formula that we just derived. K sub P will equal K sub C times RT raised to the delta N sub G, where it's R times T, that whole term that is raised to the exponent there. R will be equal to 0.0821 liters times atmospheres over moles times Kelvin. Our temperature that we plug in to our T also has to be in units of Kelvin, the absolute temperature scale. So if we look at our reaction, let's determine how many moles we have on our reactant side of gases and how many moles we have on our product side. So on our product side, we have a 1 out in front of our CO2, so 1 mole of CO2, plus we have 3 moles of H2. So we have a total of 4 moles on our product side of gases. We're only looking at gases here. And on our reactant side, we have a 1 out in front of our water, it's gaseous water, and we have a 1 out in front of our methane. So we have a total of 2 moles of gas on our reactant side. We can calculate the change in the number of moles of gas, or delta NG, by taking the difference from the product side, so we have 4 moles of gas, minus the reactant side, 2 moles of gas. So the difference between the two of them ends up being 2 moles of gas. That means we're going to substitute in for our exponent of delta NG 2. So our K sub P will equal our K sub C, which is 3.8 times 10 to the minus third, times R, 0.0821. And we'll just leave off units for now because K sub P and K sub C don't have units, so it can be confusing to try to break down the units at this point. Times our temperature in Kelvin, so times 1000, and that'll be raised to the second power here because that's what delta NG was. So our K sub P comes out to being 25.6. In this case, it's a larger value than the K sub C because we made more moles of gas on the product side. Let's try another example. At 1000 Kelvin, K sub P equals 158 for the decomposition of nitrogen dioxide. We have our balanced equation. 2 moles of nitrogen dioxide decompose to form 2 moles of nitrogen monoxide and 1 mole of oxygen gas. What is the value of K sub C at this temperature? So our equation is K sub P equals K sub C times R times T raised to the delta NG. Looking at our balanced equation, we have 2 moles of gas on our reactant side, and we have a total of 3 moles of gas on our product side because we have 2 moles of nitrogen monoxide and 1 mole of oxygen gas. And on our reactant side, we had 2 moles of nitrogen dioxide gas. Our delta Ng then will equal the moles of gaseous product, so 3 moles of gas, minus the moles of gaseous reactant, 2 moles of gas. And that difference in this case is 1. So we're just going to have an exponent of 1 that we substitute in for delta Ng. We're going to want to rearrange and solve for K sub C. So K sub C will equal K sub P divided by RT raised to the delta Ng power. And our K sub P was given to us, 158. R times T is going to be 0.0821 times our temperature in Kelvin, which is 1000. And that will be raised to the first power because that was our value of delta Ng for this reaction. Our K sub C ends up coming out to 1.92. Once again, K sub C is less than K sub P in this case because we had a reaction that produced a larger number of moles of gas. So far, all of our reactions have had species that were all in the exact same state of matter. This is referred to as a homogeneous equilibria, meaning all the reactants and products are in the same phase, such as all of the reactants and products being gases, or all of the reactants and products being aqueous solutions. Whatever it is, as long as they're all in the same phase, we can refer to it as a homogeneous equilibria. But there are also heterogeneous equilibria, where the reactants and products might not be present in the same phase. They could be present in more than one phase. You could have a mixture of solids, liquids, aqueous solutions, and gases together. Whenever we write an equilibrium expression for a heterogeneous equilibria, we're going to actually end up leaving any pure solids and pure liquids out of the expression to calculate either K sub C or K sub P. This is because pure solids and pure liquids have relatively constant concentrations that are not changing, especially compared to the concentrations of gases and things that are in aqueous solutions. So those two get left in for our equilibrium expression, species that are gases or aqueous, but if they're pure solids or pure liquids, we leave them out of the equilibrium expression. Here we have some examples of reactions that are heterogeneous equilibria. So we have PCl5, which is a solid, in equilibrium with PCl3, which is a liquid, and chlorine gas. So PCl5 represents a pure solid, and PCl3 represents a pure liquid. When we write the equilibrium expression, we don't want to include those two things in it. We're still going to take the ratio of our products over our reactants, but in this case, K sub C will be equal to one of our products, Cl2, which is a gas, and it would just be raised to the first power because there's a 1 in front of it in the balanced equation. We don't have anything else to include because we're not going to include our pure liquid and we're not going to include our pure solid. So really in this case, the Cl2 would just be over 1 for our reactants. So we can simply write this as the concentration of chlorine. For our second one, we have solid calcium oxide reacting with sulfur dioxide gas plus half a mole of oxygen gas to form solid calcium sulfate. The calcium oxide and the calcium sulfate represent pure solids, so those do not go in the equilibrium expression. So our K sub C will be equal to, it's going to be products over reactants. We have no products to really write, so we just put a 1 up there. And for our reactants, we have SO2 gas, that'll be raised to the first power, and O2 gas, that'll be raised to the 1/2 power, because we have a 1/2 in our balanced equation. So sometimes you can have nothing in the numerator, or sometimes you can have nothing in the denominator, especially when you're dealing with heterogeneous equilibria, where you might have some pure solids or pure liquids in the reaction. Let's try another one. Write the equilibrium expression for the following reactions. In the first one, we have calcium carbonate, which is a solid decomposing into solid calcium oxide plus carbon dioxide gas. So looking at this, calcium carbonate is a pure solid. We're going to leave that out. calcium oxide is a pure solid, we're also going to leave that out. The only thing we're going to include is our gaseous carbon dioxide. So K sub C will equal the concentration of our product carbon dioxide gas just raised to the first power. That would be written over 1 because we have no reactants to include. So simply we can just write concentration of CO2 would be equal to our K sub C. For our next one, we have gaseous P4 plus 5 moles of gaseous O2 forming tetraphosphorus dicoxide, which is P4O10, and that's a solid. So we don't want to include that pure solid in our equilibrium expression. So in this case, K sub C will equal 1 over our reactants. We're going to have P4, that'll just be raised to the first power, times the concentration of O2, and that'll be raised to the 5th power because there's a 5 out in front of our O2 in our balanced equation. So our equilibrium expression here is K sub C equals 1 over the concentration of P4 times the concentration of O2 to the 5th power.